Okay, guys, our topic today is we're going to deal with functions. And like I said before, I hope you understand how mathematics work in terms of how you apply it, and simple examples, you must have them at this stage because you're grown up. So the course which you're going to do is first going to address exactly that. You're going to have a course which at the end of the day you must be able to use, maybe modeling something or describing some situation using mathematics. So before we can do that, the concept of functions or a function is very important for us. So I'm going to deal with that first. So talking about the function, I think the first question to ask, what is a function? So I'm not going to ask you to tell me what a function is, because I know we're going to waste a lot of time with that. First of all, let's note that if you're going to talk about functions, I think one of the things you must have an idea is what is a set. Like I've said there, a set, like you are a set yourself, like here I've written that a set is a collection of any objects or any entities put together according to a certain criteria. A collection of any object or entities put together according to a certain criteria. It could be a property which is shared by those objects. It could be a color which is shared by those objects. It could be a shape which is shared by those objects. Anything. Then you collect them together according to that particular criteria. You say you've got a set. Like, for example, examples of sets. We've got this natural numbers. The numbers which you use first day at school, counting. 1, 2, 3, 4. That's a set of natural numbers. And then we've got something like this. What is that? A set of vowels. All together. A set of vowels. And the next, I think, from we know that the vowels are actually from the alphabet. All together. So if I were to talk about the set of letters of the alphabet, this is what I would say. I would write here, talk about the alphabet, I would say, let's say, I write here set B, and say A, B, C. I'm listing actually the members of the set. Then go on there up to X, Y, and Z, and that. All together. So that is the alphabet. Now, if you look at the alphabet in terms of A, in terms of the set A, I think you can see that the set A is actually contained in this alphabet. Then to express that, we say A is a subset. That symbol there says it's subset. I think you can write the word subset. Is a subset of B. Now, if I want to, what do I mean there? I mean, if I've got A here in A, small letter A in A, is actually A also in B. Now that implies, or that means that A is in B. Obvious. If a letter here is a vowel, it must be from the alphabet. Altogether. So then you express that thing by saying that is a subset. Altogether. This is what we have here. Like I repeated this thing here. That's what we have there with natural numbers there, vowels, and that's the alphabet. And then that set is further. So now this symbol, this funny E, like that, you can read it as belongs to. This symbol can read it as belongs to. Belongs to, or is a member of. Like, for example, I can say here 2 belongs to the set of natural numbers. So what these entities here in the set, we call them members of the set or elements of the set. So 2 is an element of that one. But if now I talk about A in relation to natural numbers, is that true? Is that true? No. So to express that no, I would say that A does not belong to the set of natural numbers. Altogether. So you must try to understand these symbols like that, or how to mean that. Now, about sets, we can do a lot of mathematics which can take us the whole semester. But we're not going to do that now. What we're going to do here is just going to look at those few things, so a few ideas which we need for this thing. If anything else about sets is needed, I'm going to remind you or show you as we go on. Is that fine? So now just hold on the fact that a set is a collection of certain objects grouped according to a certain criteria. That far? Is everybody fine? Okay. Then, talking about functions. Functions normally happen between sets. We can actually illustrate the idea of a function. Note that I haven't even said to you what is a function. I'm just using the word. But we're driving towards understanding what exactly a function is, isn't it? So let's say I've got two sets here, A and B. I can relate, I used R there just to mean that I can relate elements of A with those of B. So what I can say maybe there's a relationship between what? Elements of A and those of B. So let me see which elements are related. Let's say 1 is related to 1. And the 4 is related to minus 2. 4 again is related to 2. And the 25 is related to 5. And the 9 is related to 3. And the 0, 0. All together. Okay. So I can just say that arrow there of that relationship takes 4 to 2 and it takes 4 to minus 2. All together. And that arrow there takes 16 to, there's nothing there which we can relate to, isn't it? We're talking about that set, what that set contains those elements altogether. So 16 will be left like that. There's nothing we can send it to in this set. Altogether. So remember, I'll talk about only those things which are in the set. Okay. Now when you come this side, there is another relationship which I said R2. Then 4 goes to 16. And the 2 is sent to 4. And the 7 is sent to 49. And nothing else. There's nothing which else what I can do here. But I think if you look at this kind of relationship, you can more or less, if you are familiar with numbers, you can more or less try to see how these things are related. And you can even maybe try to express that thing mathematically, that 4, as it goes to 16, it's actually 4 squared equals to 16 altogether. So, but I don't have something here which I can square to get 19. I don't have something here which I can square to get minus 14. So I leave that thing. So the relationship is only between those elements there. Altogether. Okay. So now, there's a very, very special difference between what we see here and what we see there. Who can tell me? And that first one, you can see that one element can be related to more than one. In other words, more than one arrow can part from one element. And then this, what is this saying? It's saying this is not a function. So I'm showing you something which is not a function here. This relationship cannot be described as a function. But when you come here, you get an element here. Let's call, there's elements here. Let's call each one of them x, which belongs to x. And that element, the elements we have got here, they're only sent to a unique element. 4 is not sent to 16 and it's not sent to minus 16. It's only sent to 16. 7 equally is only sent to 49. And the 2 here is only sent to that. So such kind of relationship is what is the relationship we're going to call a function. You understand what I'm saying? So in this case here, when we start introducing the word function, we're actually introducing some kind of discrimination between two types of relationship which can exist between two sets, whereby one member can be sent to more than one, and the other, this one is one member can only be sent to a unique element of the other set altogether. Then in that case here, the members of y here are called y, little y belongs to capital letter Y. Then to express that there's a functional relationship between these two here, or the functional relationship between these two, you're going to say here y is equals to f at x. So in this case here, we can say f at 4 is equals to 16 altogether. And when we say this is is 4 squared. What this is telling us is giving us a rule or a way of forming the value of the function altogether. Then in this case now, even if it was not there, if I were to say to you, fill in the something here, which I will send square root of 2, you can now tell me, what is it? You have got square root of 2 here. I want something here which is going to be sent to which square root of, what's going to be? 2, because you're going to say now, what this is saying here is saying that x squared. Now, what you take from this set, you must square it altogether in order to get that. So this, we can call it the law of formation. Formation of what? Of the values of the function. Altogether. Formation of the values of the function. Let's do this. Because if I've got y is equals to f at x. How do I read this? I read this as value of the function. The function in this case is f at x. So we simply read this as f at x altogether. So that is function. Then quickly there, this x here, as it's sitting there, is going to be called the argument of the function. That's the argument of the function. And this x again, being the argument of the function here, is called again the independent variable. Why variable? Because x assumes different values altogether. Okay. Now, y here? We're never going to know y unless and until we know x. We're going to compute y from x. So y here is going to be called a dependent variable. A dependent variable. Altogether. So now this f function here, it can be anything. I mean, I'm not talking to people who don't know mathematics here. I'm talking to people who know some bits of mathematics. It can be a trigonometric function, can be an exponential function, can be a linear function, be quadratic, all those kind of things altogether. So then each function, depending on its type, is going to give us the law of formation of the values of the function. Altogether. Okay, then let's go this way. Now, again, what we did here, if you reflect what we do, we can pay these things like this and put them like this. 4, what was this? 4, comma, minus 2. You know, as a function, I can represent it schematically as I represented it there. I can represent it also as pairs. And then have 4, comma, 2. In this case, I'm talking about relationship, just a relationship, I can do that. Then I can go now 25, comma, 5, and 0, comma, 0. So looking at these pairs also, I must be able to tell whether this kind of relationship is a function or not a function altogether. So once I see a first coordinate relating to more than 1, paired with more than 1, then I know that's not a function. But when I come here, I know I can relate 1 with 1. And then 2 with 4. And 7 with 49. And then what? 4 and 16. 4 and 16. And according to our filling in there, we can relate square root of 2 with what? With 2. So you get square root of 2 with 2. We only realized that we could relate square root of 2 with 2 when we had seen the law of formation of the values of the function altogether. So then 2. Altogether. Okay, so now I hope it's clear, guys. Once you've got two sets like that, you can maybe establish that there's a function between the two sets, or there's no function between two sets. When there's a function, when there is when you're given a variable, independent variable, you must assign only a unique value that side. Then the next thing, which is very interesting for you as engineers, this is the kind of thing. When we're talking about function, this is very, very important. I can write here system. System is one word which is abused by a lot of people. They talk about it, but they don't know what a system is. People just say system. You hear people complaining sometimes, hey, this system is not working. Then you ask, what is a system? The person looks up. Can you tell me, as engineers, what is a system? What is a system? Aha. So what do you mean when the street want to always say, this system is not working? They stole my system. Some people say, they stole my system in my house. What is a system? Funny things, eh? Right. Saying it in the simplest, maybe simplest way, which could be understood by any even grade 1 child, is that a system is a collection of different units, maybe discrete units like that. But this collection, these units are connected in such a way that they will perform a task. Do you understand? A government is a system. What are the units? The departments. What is the task going to do? To run the issues of this country. It's a system. Altogether. Then you say your computer is a system, this is a system. If you look at the computer, open it, it's small discrete units. They are interconnected wires and all it. They perform a task, the task that computers do. Altogether. So you must learn it that a system is a collection of discrete units which are interconnected in such a way they perform a task. I didn't say to perform tasks. I said a task. Then systems can be interconnected. Then one system can be a subsystem of the other. Okay. But each system will perform a task. So a function as a system, what we are saying is, if we put an input here, actually a function is kind of an input-output system. If we put an input here, there will be an output here. Because being a function, then with the output here will be unique, and that output here will be y, and just to show that this y is delivered from this x, we say y function of x as a value. Altogether, let me check you guys here. Which one of you would like this kind of a machine or this kind of a system? Here is a system. We don't know. Actually, it's illegal to call it a system because it's not a system. But I'm just supposing we thought this was a system. Like, for example, we put maize grains here, maize here. You know what is maize? Maize. You take the grains of maize, you put them here. And when you come out here, you get something like this. You are never sure whether you're going to get this or that. But what is this? Cement. And what is this? Maize meal. Such kind of thing, nobody prefers it, isn't it? Altogether. So that is kind of a system which is not actually behaving like a function. Altogether. In this case, it is actually not a system, because a system does this kind of a thing. Is that right? So by all these things I'm saying now, I'm trying to knock down into your system, this idea of what is a function, how does it work. Before you look at any particular function, you must understand that the concept, what is a function, how does it work. All together. Okay, now functions normally in mathematics, we represent them in using graphs, plotting. Like if we look behind there, what did you have here? What did you have here? With 4 minus 2, 2. Is that right? So if we come here, let's count here 1, 2, 3, 4. Then we have 2 here and minus 2 here for that one. So this 4 is assigned a 2 and a minus 2. Altogether. then we actually say that is not a function. Are we together? Because of that. So, but a function, what will happen now? A function, let's look at the second setup. This one. You'll have 1 associated to 1. So, let's see. We'll have 1 here associated to 1. And then the next one, we've got 4. Can you write those values down? 1, 1, 4, 2, 4, 7, 49, 4, 16, square root of 2, that. Write them down. So you can plot them once here. We said 1 to 1 and 4. Sorry? This is 1 to 2. Oh, okay. Let's just do this. So 1 there, 1. Is it right? And the next one, what's the next pair? So 7 to 49. So 1, 2, 3, 4, 7. 7 will be out of the graph anyway. Is that right? But you know this one. The next one? Come again? 4 to 16. There's 1, 2, 3, 4 here. 16 will be 2, will be 1, 2, 3, 4, 5, 6, 7. Let's just count in 2s maybe. So 16 will be somewhere up there. Just roughly, please. I need roughly 16 there. And next one? 7 to 49, we did that, did it? Yeah. But 2? 2? Square root of 2. Square root of 2 is 1 comma something to 2. It will be somewhere there. All together? Okay. And then the next one? That's all. But now what I want you to emphasize this one with you here is that if we've got a function, what actually is going to happen is, if we've got a function, this is what's going to happen. From the point which is made by that pair, we can actually draw a parallel to the y-axis through the point which was assigned that value. This one here was assigned that one there. We can draw a parallel there. There again, we can draw a parallel to the y-axis and so on and so forth. So what I'm trying to introduce you to here is that if I have a graph, how can I tell that this is the graph of a function or this is not a graph function? What we use there, we use what we call the vertical line test. This is what we call vertical line test. What do you have here? Got two functions here. Y is equal to square root of 2. Y is equal to square root of 2 and the y squared. Now y squared is a function. I think everybody can see. If we take a value here and we go up to the graph there, that point there would have the coordinates x and the same coordinate y will be f at x and close. So please understand this thing. Whenever on the graph of a function, you must know that the point in which you are sitting on which you are pointing to has got two coordinates. One coordinate is x and the other coordinate is f of x. And the other coordinate which is f of x is actually the y we are talking about here from the y-axis. All together. So now if you do that, if you now draw a parallel to any point on the graph here, you will see that that parallel will cut the graph only at one point. Let's focus only on the black graph. So we've got a point here. Then we draw a line here parallel to that. That line, as you can see, it cuts the graph out in one point. I'm talking about the black graph. But check, for that same point, when you talk about the red graph for square root, the square root is the one which took 4 to minus 4 to minus 2 and 2. So now if we do that, if this was a 2, this would be, if this was a 4, this would be 2 and minus 2. So the red graph is not graph of a function. So when somebody comes in, test and give you all sorts of graph and say, establish which one is the function, you must do what we call the vertical line test. And then you decide this is a function, this is not a function, this is a function, this is not a function. Are we fine there? Okay. Any questions? Any questions? Okay, now let's talk about examples. Examples of functions which you have seen at school. Let's talk about examples of functions you have seen at school. Got a line there, the y-axis, the horizontal axis there. This is x, and this is y. Are we together? Okay, that arrow is not very visible there. Let's make it visible. That's the thing. And normally we will talk about this being an origin. Like examples of functions, the simplest function we can ever come across for me is the constant function. So y is equal to f of x, and that fx is equal to a c. We call that a constant function. C there could be 5, could be 6. So now if c is somewhere there on that real number line, then the graph of that function will look like this. All together? Okay, so all the pairs which we've got here, you must notice that all the pairs we've got on this line are going to be pairs x, comma, c. That's a constant function. That's the simplest function we've got. And then the next function we've got, or let's say the next maybe simplest function, a bit more complicated than this one. Which one do you have? Let's take to your experience from school. The linear function. So got y equals to m x plus c, which could be 2x plus 1. Altogether, we know that the kind of function will cross the coordinates at 1, and it's got gradient 2. Remember, the gradient is y2 minus y1 over x2 minus x1, and that is called m. So from any point we get there, we're going to have 2 over 1. So which means we'll move 1 unit this way, and the 2 units up that way, and then next thing what we have a line between these two. There is a line. All together. That's it. So then from there on, we've got quadratic functions. In this case, this is power 0. Remember, this x is c times x to the power 0, and here is 2 times x to the power 1. Then you get the quadratic functions, which are x squared plus maybe, let's say, a x squared plus b x plus c. As you can see from there, I'm counting in terms of powers of x, 0, 1, and that. Then you can also go to powers up to, let's say, x to the power n plus whatever we've got there, the terms. All together. Then what we're talking about there, we're talking about what we call polynomials. All together. Whereby this one is a binomial, and this one is a trinomial, and so on and so forth. All together. We're talking there about polynomials. Polynomials. All together. Good. Then after polynomials, I think after polynomials, the next functions we've got are functions we get by playing around with polynomials. How can you play around with polynomials? You can multiply polynomials, you get polynomials. You can add polynomials, you get polynomials. The only thing new you get when you play around with polynomials is when you get what we call rational functions. Let's say here, r of x, something like this. X squared plus 1 over x minus 1, and the x plus 2. All together. Okay. I don't know, maybe you didn't think about this thing, but you should have thought about it, maybe not, but then I'm reminding you. Look at what is beautiful about polynomials. What beautiful formulas. Get any polynomial, you get any x, you get a value of the polynomial. Isn't it? Do you see that? Any polynomial expression like this, you get any function y is equal to px, which p is a polynomial, you can get the value of it. But once you play around a lot and get to rationals, then there's a problem. This function, I cannot get values for all x. Remember, x here is what you can call a real number. Maybe I'm saying something very strange to some people. Do you know what is a real number? Huh? What is a real number? You don't need to explain to me, but the teacher must understand what a real number is. Yeah. Real numbers, let's start with natural numbers first. What is a natural number? We've already seen that. 1, 2, and so on. All together. And then, whole numbers. What are whole numbers? 0, 1, 2, and so on. Is it? Everything else which is natural. Then integers. All these are number systems. These are different types of number systems. They are related, of course, but the number system. And number system of natural numbers, all numbers, and the integers. What are integers? We've got 0. Yes. What else? Plus 1 and minus 1. And plus 2 and minus 2. And plus 3 and minus 3. And so on. All together? Okay. Then we get what we call rational numbers. And this is what is the symbol for rational numbers? What are rational numbers? When you have got a brother at home, your mother buys you a sweet or a chocolate, what do? You break it into 2. You actually got a number there to represent that kind of breaking. You get a 1. You get 1 piece out of 2. Then you start coming up with what we call rational numbers. Numbers which look like this. Whereby P and the Q, they are both integers altogether. And under what conditions? Under what conditions? P and Q can be integers. That's enough. Come again? And then Q mustn't be equals to 0. Why? Because the first commandment says, thou shalt not divide by 0. All together? Yeah. That's the thing. Thou shalt not divide by 0. Now, once you've got all these beautiful things like this, we still have got a problem. But I think you must remember this thing. It's from school. Remember, all what makes me talk about this thing is because we want to make sense of what are real numbers. All together? Okay. So, there is what we normally use to picture numbers. What we call number line. We've got a reference point there, 0. We've got 1 there. We've got minus 1. Sorry, minus 1. And we've got 2, just roughly, that's right. 2, minus 2, 3, minus 3. Now, once you've got this kind of thing, we've got the rational numbers. Yes, we can have the rational numbers here, like half, minus half, minus 3 halves there. And you remember also these numbers, you can also take them in this form, or you can take them to what we call decimal numbers, whereby half is 0.5 altogether. But all is still the same thing. Those are rational numbers. But when you start doing Pythagoras at school, Pythagoras, then you take a right angle triangle like this. And the Pythagoras says a squared plus b squared is equal to c squared, isn't it? And then this one will give you 1 squared plus 1 squared is equals to 2, isn't it? So if you say a squared plus b squared is equal to c squared. All together. Actually, this length here is going to end up being what? Square root of 2, isn't it? Square root of 2, because you're going to have 1 squared, this length is going to be, like now if you want C here, what are you going to say? You're going to say C is equal to the square root of A squared plus B squared. So similarly here, this C is going to be C being equals to 1 squared plus 1 squared is equal to square root of 2. And suddenly then you discover that this number, you can never put it in this form. It can be proved. If you really want to get the proof, you can get a book with mathematics which can show you that this thing can never be put this way. We don't have time to do that, but the most important thing that this is never proved. But where is this thing? Where is this number? All what you can do, you can take this parallelogram, this triangle, sorry, and they put it here. The length here is 1, and they put it there, and they have 1 there and the 1 there. This is minus 1, but the length is, there's no sign. It's minus 1. Then you do that. So which means this is what? Square root of 2. Now if you do that, then you rotate this segment. Now the segment is holding a picture of a number, its length. So now if I rotate it this way, you will see that this segment will come somewhere there. Then the square root of 2 is there. Then we start realizing that with all the integers, the natural numbers, the rational numbers, we have got other things which are not rational numbers. Are we together? So those things which are not rational numbers are those things like, I'll use this thing now for things which are not rational numbers. Those are things like square root of 2, square root of 3, pi, the natural base for the natural logarithm e. Maybe you don't know about this one, but if you don't know, it's not a problem. We're going to talk about it later. And so on. So all these are numbers which are on the number line, but they cannot be presented as p over q. And we call that irrational. But check that. These numbers, they are all on this number line here. So now when you take those rationals together, this is another symbol which is used in sets. When you put that symbol, you mean you bring them together, you make a union together with those which are not rational. What are you going to get here? You are going to get, you take this, you put it here, then you get rational numbers. All together. But you must check something here. Is 2 a rational number? Is 2 a rational number? Is 2 an integer? Do you agree with me? 2 is an integer. Is it a rational number? Say yes. Yeah. Because 2 is equal to 2 over 1. Are we together? So what I'm trying to say here, actually everything which is an integer is actually rational. So what I'm saying an integer is a set which is a subset of rationals. Do you agree with me? Then when you go to the whole numbers, remember the whole number started where? At 0. Are they integers? Are they integers? Then we've got a serious problem. People don't understand numbers. These whole numbers, 0, 1, 2, 3. Are they integers? Draw the number line for integers and see whether we're going to have a 0 and 1, 2. That's what we said here. That's what we said. The integer is 0, 1 and minus 1, 2 and minus 2. So the whole numbers are what? Are the 0, 1, 2 and that. So all numbers are integers. Are we together? So then what are we saying here? We're saying that the integers, the whole numbers are actually part of the integers. The natural numbers. Natural numbers, if you want to tell you, just drop this 0. Drop this 0. We've got natural numbers. Are they whole numbers? Are they whole numbers? Yes, they're whole numbers. These just whole numbers. We just removed 0 from whole numbers. What will remain with are whole numbers still, but they also are natural numbers. All together. Okay. So then we've got here saying this is that. So now once we've got this kind of a chain up to there, on the number line we've got some kind of holes. Square root of 2 is not here, pi is not here, and all those things. So once we discover the irrational numbers, then we've got these real numbers. Then we fill up the number line. It becomes what normal people call a continuum. In other words, you can draw it continuously without lifting a pen. You understand what I'm saying? All on that number line here, everything I touch here, I look at it as a picture of a real number. But a real number is made out of all these sets. So then here now we're going to have what? Real numbers. So guys, if you don't understand real numbers, you take that book, you look at the section which talks about real numbers. Most important things, real numbers, the rules of operating with real numbers, the absolute values, all those things must be very, very like fresh in your head. All together. So now, when we are defining a function, I've already shown you before. A function here is graphed here on a system of coordinates, x, y coordinates, whereby this x-axis is actually what we call a real number line. So we're looking at all the numbers on the real number line there. Then, how did we come to this? Talk about numbers. We came to this when we talked about, when we look at this kind of a function and say, this is a rational function. Rational function. Why rational? It has got a structure or a skeleton of a rational number. So we call it a rational function. That's a rational function. So what I was trying to say to you is that when you've got polynomials, any value of a real number you pick, you can calculate the value. There's no problem. But that doesn't happen when you deal with the real number. The what? Rational functions. Then what do you do? Not only rational functions, also with other functions. Then what do? We start seeing that if we take some values of x here, this expression is not going to be valid. For example, which number can you pick here to get r of something and you're not going to get a value? Warning. Something like this is not a number. All together. And something like this, a not equal to 0, like this, is not a number. And something like this is not a number. So now when you look at this kind of a function, before you talk about it, you must look at it very, very carefully. And this thing takes us to what we call the domain of a function. The domain of a function. Let's go. Let's say domain of a function. Domain. Domain of a function. In simple words, what am I going to call a domain? Or when I'm going to say x is in domain of a function, let's write this. Let's say the function is f of x. The function is f of x, and the function is x squared over x squared minus 1. Then I'll write df to mean domain of the function f of x. Now, when am I going to say x belongs to the domain of f? I'm going to say x belongs to the domain of f only when f of x is a defined value. What do you mean about defined value? I mean f of x makes sense to me as a number. What is what I'm saying? I say f of x is a defined value when f of x makes sense as a number. 0 over 0 does not make sense as a number, so this is undefined. A number 4 over 0 is not a number because it's undefined. Infinity over infinity is not a number because it's undefined. So then question, is 1 in the domain of f? We're talking about this f which we've got here. Question mark, I'm putting a question mark there. I'm saying is 1 in the domain of f? Check that. So how are you going to check it? You're going to take f at 1 equals to 1 squared over 1 squared minus 1, which is going to give us 1 over 0, undefined. So 1 is not in the domain of f. Say this answer it here. Say 1 is not in the domain of f of x. Am I making sense? Yes. Okay. So can somebody hunt for another number which is not in the domain? Can you check for another number which is not in the domain of f of x? Think, push a pen against your paper, test, make tests. Come again? Negative 1. Because negative 1 squared will give us 1. And will give us that. So again, what it's saying here is that minus 1 is not in the domain of f. Are we together? So now, somebody now will say, give the domain of f of x. Give us the domain of f of x. What are we going to do? We're going to say, domain of f of x is a set. Remember, we use these brackets as boundaries of a set, or listing members of a set. We use these brackets. So what will be this set? This will be a set of real numbers. In other words, that x is a real number line. All together. Such that this line, as I write it there, you must read it as such that. And that line also can be replaced by something like this. It can get it such that. Such that x is not equals to plus or minus 1. So when I give that set, that is a set. It's a set of numbers. The condition they satisfy, the condition which is common among those numbers is that they are all different from x from plus or minus 1. And you will see that those kind of numbers will always give us a value which is defined for this function. Guys, am I making sense? Does everybody now understand what you mean by domain of a function? Yes. Are you sure? Yes. Are you sure? Yes. Let's check whether you do understand. Let's check whether you do understand. Let's have a function here. Y equals to f of x equals to 1 over x. Can you write yourself a domain there, the domain of that function? Write it yourself for yourself, then you read it to us. Obvious, this function is graphed on a system of coordinates. And the coordinate, the x, this is an x, which is a real number line. And this is what? A y, which is also a real number line. So can you give me the domain here? Who can give me the domain? Can I have one person tell me what is the domain? Yes, my children? We're checking what is the domain of this function. This is a 1 over x. You must give me the set of values which are real numbers, which will make this thing make sense always. That set is going to constitute what we call a domain of the function. Who can give me the set? Yes? A set of x's, of course, all these are reals. Set of x's which are real numbers such that the x not equals to 0. Are we together? Yes. And then I think you remember that function. This function will do this. This function will do this. It will be graphed this way. And the graph goes also this way. And this is an x-axis. And this is a y-axis. And then the set of values of this function, they don't include 0 because this graph does not touch 0. the set of values, now I'm talking about the y values, which are equals to f of x. I think you can see that these f of x, they are all different from 0. Now these values here, they are going to be described as values which belong to the range of f. To the range of f. So now we can get now R for range. Range is this way. Range this way. So now when you write R, F there, we're talking about the range of f. What are these now? These are y values which are real numbers, such that y is not equal to 0. So that's now we call range of the function. Now let's look at this one now. F of x equals to x squared. Tell me. We'll talk about this f now. We'll talk about this f now. This one. Notice this is a kind of a polynomial, or in this case a monomial. A polynomial which has got only one term. This. What is the domain of this? What is the domain of this? So now we're talking about the domain of f. In this case, f, we're talking about this f. What is the domain of this? Come again? R except 0. Okay, let's take f of 0 and see what happens. F at 0 equal to 0 squared is equal to 0. This is defined. So that's not true. What's the domain of this? Sorry? X is an element of real numbers, isn't it? So we can just say the x is such that x is a real number. Or we can just say the domain is equal to the real numbers. Otherwise, that function delivers values for all real numbers. All together? Yeah, that's the domain. Then let's check something now. What is the range? What is the range? The range are wise. The range are wise. And they are real numbers. Of course, if you score a real number, you're going to get a real number, isn't it? Okay. But then such that, can you draw the graph of this function? Can you draw the graph of this function roughly? Draw it. I think it's like this. Yes or no? So then what will be the range? The range, I'm talking about those y's for which I've got an x which I can square to get that y, isn't it? So, which y's are those? Such that condition y good greater or equal to 0. We just saw it here. When it's 0, it delivers 0. When it's 1, we're going to get 1. When it's minus 2, we're going to get 4. When it's 4 is 2, we're going to get 4. So which means this is only going to deliver what? Positive values. That is the range. Are we together, guys? Okay. Are we together? Okay. So please note, we have started from the beginning to find the function, the concept general, what it represents. Then we have started now taking particular functions, polynomials, rational numbers, polynomials, which are very beautiful functions, polynomials, because they always give us values. So they're defined everywhere. But when you play around with polynomials, multiply, divide, then you get to rational functions. Then we start having problems. We have to look at the denominator and check whether we don't have something, an expression where we're going to have this thing undefined. So all those points where the rational functions are undefined are going to be called the points outside the domain of the rational function. But otherwise, the polynomials, everything is in the domain of polynomials. I think for today, I'll stop there and say thank you for listening.